In a June 20th, 2021 workshop on autonomous driving at CVPR 2021, Andrej Karpathy live-streamed a keynote talk. Not only did he discuss Tesla's goals in creating Tesla Vision and the ways in which Tesla can automatically grab and label data, but he also discussed the latest neural network architecture, how it's built, and why it's so effective. Let's continue exploring Dr. Karpathy's talk. Hey y'all, it's Dr. Know-It-All. So first of all, this shirt, the man, the myth, the legend, that's from my kids for Father's Day, so I told them I would wear it as one of my videos, so there you go. Anyway, hopefully it was tongue-in-cheek on their, actually maybe hopefully it wasn't tongue-in-cheek on their part, maybe they actually think that, but I kind of doubt it. So anyway, you should definitely watch the first half of this video, this two-part series, if you have not, which goes over the goals, the strategies, automated data labeling, all of that kind of stuff. It's sort of a setup for this episode. I'll put a link to it up here. I'll also put a link to it in the description in case you need to look for it that way or something like that. But anyway, I highly recommend that if you haven't watched the first half. If you don't care and you can watch it in either direction, that's fine. You can watch this, but you just may be confused by a few things. So anyway, you've been forewarned. So what are we going to do in the back half of the double header here? Well, in this half, we're going to take a dive into the neural network architecture and look at some examples of how well this system actually does in the real world. It's definitely a geeky episode, but it is super cool.
So we have an incredibly good AI team that is designing the neural network architecture. There's basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by a transformer, by a recurrent neural network, or just by 3-dimensional convolutions. We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks, that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at that time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I am someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals. And so I can work in isolation to some extent and actually get something to work pretty well. And then once in a while, so basically the iteration scheme is that a lot of people are fine tuning, and once in a while we do an uprev of all of the backbone end to end. And so it's a very interesting sort of mechanism because we have a team of roughly 20 people who are, I would say, training neural networks full time, and they're all cooperating on the single neural net. And so what is the workflow by which you do that is pretty fascinating and continues to be a challenge to actually design efficiently.
So that was a long clip, I know, and there's a lot to unpack there. First of all, I want to talk about their AI team. The core AI team, it seems like, is only 20 people-ish, as Karpathy said, and that's a pretty remarkable number. It's a very, very small number of people, but in some ways it makes sense to do it that way because of the way they're working on everything, and we'll talk about that more as this episode goes on. But it's important to think about the more people you have, the more difficult logistics become. And it sounds like logistics are already an issue in terms of working with multiple people on multiple heads of the neural network that we're going to talk about again. But it seems like 20 might be kind of an optimal number for them. They have enough people that everyone can focus on one area, but not so many people that there's a lot of dead weight and a lot of confusion over who should be doing what. All right, so let's look at this neural network architecture slide that Karpathy put up. Unfortunately, everything is really blurry in this live stream, and it really sucks because it's difficult to see a lot of the information. I did my best to clean up this image, and I'm going to put it up here so you can look at it as I'm talking about it. But basically what you've got is it looks like you've got the 2 chips, right? So there's 2 SoCs on the Hardware 3 full self-driving board as a means of redundancy. And it looks like they've put up both of these chips on the neural network architecture slide. So anyway, I think that the left and the right, basically at the bottom, are the same thing more or less. I don't know that for a fact. This could be done on each chip, and then it's actually maybe 4 of these heads at the end, but it looks to me like we've got something along the lines of each of the SoCs is processing these things in parallel. But anyway, starting at the top, you get your input images. So there will be 8 of those because there's 8 cameras, and obviously not all of those are shown. There's only 3 of them with a ... But anyway, you get your input IMG or image, then you have an image extractor. And the extractor, as Karpathy said, is more or less a traditional ResNet type of architecture. And this is something that's been around since, around 2012 or so, or in other words, ancient history in the neural network world. But that's really interesting because that's using, not off the shelf, but quote unquote off the shelf type of neural network model, which is very, very cool. It means that they're not, again, inventing things from whole cloth. They're standing on the shoulders of giants, and that's a really, really cool part about this and a way to leverage work that other people have done. So after we get each of our 8 images and we get through our image extractor, we go down to the multi-camera fusion step. So what that is a way of stitching all the cameras together into one surround image. And as Dr. Karpathy says, this uses a transformer neural net, which is a different type of neural network, much, much newer than ResNet, but it's also a fairly established technique. And then if you sort of look back up to the top, you see a thing that says tensor video queue, and then, T-1, T-2 to T-N. And what that is that's a way of putting time together into this whole thing. So again, if you haven't seen episodes on this, you should definitely check out episodes about this. I've got an entire playlist about neural networks and the architecture and the way they're built and everything. So you should definitely check that out when you have a chance also. But anyway, a tensor is a multi-dimensional matrix. In other words, you can think of it like a spreadsheet on steroids or something. And what it's doing is it's storing each time step up to T-N steps, and then it stitches that together with the current frame. So what happens is you get all 8 cameras, they get fused together into one super camera image, and then you get N steps backwards. So at 36 frames per second, which is what he says it's running, let's say it's 2 seconds, that would be 72. So N would be 72. So you take 72 frames and you combine those. So you get one super image, but it's a super video instead of a super image. And as Dr. Karpathy said, this is done in one of 3 ways, or maybe all 3 of them at the same time. You've got a transformer network, a traditional convolutional neural network, but it's 3-dimensional, which is pretty cool. So that means it's actually doing a 3D thing. So it's probably the X and Y dimensions of an image plus the 3rd dimension, which is time. I've actually done this in some of my research also, and it really, really improves image recognition when you're working on something like that. So 3D is pretty much the way to go. They call it 4D, but I think 3D actually makes more sense because it's just a 2-dimensional image plus you're adding time to it. And the last network they use with this is a recurrent neural network, which is very important. That's how you actually include the time steps, because recurrency allows you to look backwards in time and to have that influence the present frame. So anyway, this is all super, super cool. And it looks like what they're doing is they're creating a sliding window of time where the end drops off after n frames. The end drops off after n frames, just to make that very clear. So what that would mean again is if you have 72 frames, when you get the next frame, frame number 72 goes away and you get a new frame 1 and a new frame 72. So it's like a sliding window that goes across time like that. But anyway, what that gives you is the previous n frames. They're available to the current frame to give context to what's going on now. And by the way, if you want to check out my trajectory projection episode, it was very popular back when it came out and Elon Musk actually commented on it. You should definitely check that out also because I go into much more detail about how that all works. So anyway, up to this point, we're fusing, right? We're extracting the data from each camera. We're fusing the cameras together. We're fusing the time together. But then what happens, and this is pretty unique as far as I know, is that the neural network starts to branch. Again, this is a fairly unique step as far as I know. It's definitely not the usual neural network approach, which is to keep extracting and reducing and extracting and reducing. Anyway, as Dr. Karpathy said, we've got heads and trunks and terminals. And that is extremely cool. So each head gets the same video data, right? We get our multicam fusion and our time fusion. All of that goes into each head, but each head is different. And then this data is passed from the head to the trunk, and each trunk is different. That has a specific task, like maybe one trunk is object detection, one could be object attributes, one could be the kinematics of objects, or the planning of the trajectory of the car. And then each trunk is passed on to a terminal that further breaks down these tasks. So like one terminal under detection might be for stop signs, right, for example, or under kinematics, it might be how a human pedestrian moves, which would be related back to detection of humans and then determining the attributes of said human. So what we're getting is instead of one neural network for each individual task, like finding a stop sign or something, we get what Karpathy calls amortizing. In other words, we use one sort of generalized trunk, and that trunk is designed for detection in this case or something, right? So we get to amortize detection for the thousands of different types of detection that need to happen. So rather than writing thousands of neural networks that are all running in parallel, you get to have a trunk, and then each terminal at the end, which is like a little mini model or mini network, gets to do individual tasks and have predictions out of that. So anyway, all of these trunks and terminals run in parallel. It's a little bit unclear from the talk how they communicate back and forth, as they're all pretty much running side by side at the same time, at least according to the graph. But in some way, they have to pass this information on to each other somehow. I'm not sure if it's done through time, like it goes backwards and it's recurrent, or if they're doing it at the present moment, like each frame. Probably there's enough time. In my mind, I would think that what they could do is they could pass this information on to the T-1 step, and that would feed information. So it would lose one frame, which is fine, right? That's a tiny fraction of a second. So in my guess, it would be passing this information on to the next time step as something that's recurrent, right? So it's giving it context for the next time step. But again, this might be getting way too geeky for you guys, but I'm really interested in how they're communicating with each other. It's not clear. It doesn't look from the graph like they're communicating directly side by side in the same time step. So my guess is they're passing that on to the T-1 time step at each point, but I don't know. It's not clear from the talk, so we'll have to see as we get more information about that. So to get back on topic, the trunks function as a generalized neural network for each general task. In other words, it would be a nightmare to have a different neural network for stop signs, stoplights, garbage cans, dogs, cats, people on bikes, curbs, trees, trucks, cars, and on and on and on, right? There's just too many possibilities of individual things that have to be detected, but they can all be kind of subsumed into a more general model that detects objects. And again, as Dr. Karpathy talks about, what we're doing is amortizing the forward pass. It's a way of saving power and reusing the same neural network model for all detections, and then attribute determinations, et cetera, et cetera. Importantly, the terminals, however, are decoupled. So that's the last step. Each terminal is its own thing, its own little tiny neural network model, and it makes its own decisions, and it can be worked on and it can be tweaked separately without messing up the other terminals. So working on stop sign detection, for example, wouldn't break pedestrian detection or trajectory planning, et cetera. And that's really, really important to efficiency of working on this. You don't want to go and break something that you're not even working on. Anybody who's done coding, if you've ever done things that pass information back and forth between subfunctions, you know that sometimes you unintentionally break another function when you fix one. So this is a way of keeping that from happening. All of these things are kind of siloed at the end, so everybody can work on their own little piece of the pie without messing up somebody else's work. So again, the pieces can be fine-tuned separately and with a lot of focus, and then you put all of this together from time to time to see how the system is working overall. And again, remember, we've only got 20 people working on this, and they have to do this without stepping on each other's toes. So number one, it's impressive that it's that small of a team that's amazingly lean. But at the same time, like I said, I think a lot more can be done with a small group of brilliant people as opposed to a large group with a lot of dead wood in it. As a sort of analogy, you could think on working on a text document with a team of people. It's much easier if each person takes on a paragraph after you've established what each paragraph is supposed to be about, rather than having everyone trying to edit random places of the document at the same time, right? If each person only edits one paragraph, you can then re-examine your document once in a while to make sure it still makes sense. But you don't have people making changes all over the place and then somebody else is like, what the heck, this doesn't make any sense anymore, right? Because 3 people were editing the same piece of text at the same time. So that's basically what's going on here. You could imagine, a multi-paragraph document, and each paragraph is one person working on it, and then you put it back together once in a while and you read it and you see if it still makes sense. That's, I think, a reasonable analogy for what's going on with the way that they're developing this neural network architecture. So anyway, that's an overview of the neural network architecture. Plus, remember from the last episode, we have approximately 1.5 petabytes of data. So how in the world do we feed all of that data into something and train a very, very complex of neural networks? Get it? A complex of neural networks. Why? And I'm sure this is a huge surprise to you. You need an in-house supercomputer to do this.
So we have a neural network architecture. We have a data set. Now, training these neural networks, like I mentioned, this is a 1.5 petabyte data set, requires a huge amount of compute. So I wanted to briefly give a plug to this insane supercomputer that we are building and using now. For us, computer vision is the bread and butter of what we do and what enables the autopilot. And for that to work really well, you need a massive data set. We get that from the fleet, but you also need to train massive neural nets and experiment a lot. So we've invested a lot into the compute. In this case, we have here a data set. We have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. And we have also a very efficient fabric that connects all of this. Because of course, if you're doing distributed training across your nodes, you need your gradients to be synchronized very efficiently. And of course, we are reading all of these videos from the file system, and that requires a really fat pipe as well. So this is a pretty incredible supercomputer. So this is a GPU cluster. Next up, we're really hoping that we're currently working on Project Dojo, which will take this to next level, but I'm not ready to sort of reveal any more details about that at this point. What I would like to do is I would like to just briefly plug the supercomputing team. They've been growing a lot. And so if high-performance computing for this application and for training these crazy neural networks excites you, then we would definitely appreciate more help. So please contact the supercomputing team at supercomputing at Tesla to help us build these clusters.
So as the graphic shows, this supercomputer is a beast. As Dr. Karpathy said, it's somewhere around the 5th most powerful supercomputer in the world. And it's not even Dojo yet, which is really, really scary because Dojo is going to be the next level, whatever the heck that is. So it sounds like they're probably going to take over the top spot in the world when Dojo gets released, which again, as a corollary, when you start thinking about AI as a service, again, like Amazon Web Services, if we think about Tesla AI services or TOS, oh, that's a little bit Soviet right there. But anyway, you could think about that as a service. They could make a ton of money on that after they pretty much solve full self-driving. So that's going to give them another huge revenue source in the future. But anyway, back to the mundane present 5th most powerful supercomputer in the world. It's got 5,760 GPUs. Each of them has 80 gigabytes of VRAM, which is just amazing. This is all stored in 720 nodes, or those little boxes that fit on racks. And by the way, the cost for the GPUs today, I can't even imagine how much it must cost given the chip shortage and everything and how much GPUs cost. It's crazy. But anyway, all of this together does 1.8 exaflops, or exa floating point operations per second, which is right. I mean, I remember it wasn't that long ago when petaflops were a big deal, and now we're 1,000 times past petaflops. It's just amazing. Plus, and this is super important for the training that they're doing, it's got 10 petabytes of highly addressable memory at 1.6 terabytes per second. So basically it can transfer massive amounts of data, like around an entire consumer hard drive in 1 second at a time. So it's sucking all that data in, it's pushing all that data out, and then it has massive connectivity at 640 terabits per second to keep everything synced up. So basically each one of these nodes is doing a little bit of the training, and it has to keep all of that stuff synced up. So it's got to pull in the data, it's got to spit it out to all the nodes. They've got to do their little training stuff, they've got to then resynchronize and put it back together and spit out their answers. This is really, really, really complicated. But basically what this tells us is this thing can not only calculate like crazy, but it can do input-output of data at an insane rate also. And Dojo's going to be next level. I mean, I don't even know what that entails. It's hard to even imagine how it could be better than what it is here. But Andrej says it's there, he just says they're not ready to talk about it yet. And by the by, note the little recruiting plug in the slide. So if you happen to be really good at supercomputer stuff, you should definitely apply right now. And finally, we get to the incredible Hardware 3 chips that are all in all of our Teslas right now. And by the way, I really wish I could see that graph on the left in this slide in detail, because I think it's telling us a whole bunch of stuff, but I can't see it, it's too low resolution. But anyway, the upshot of it is what they're doing is graph optimization / fusion. And this is a way for them to take a really, really big neural network model that they use for training, and they reduce it down to something that is nearly as good, but it can run on the chips that are in our cars. In other words, it's optimized and recompiled for their custom-built GPUs in the Hardware 3 chips. And by the way, as a refresher about Hardware 3, remember there are 2 SoCs on the board. In other words, there are 2 systems on chips that are redundant so that you can run them at the same time, and if one fails, you can always kick over to the other one. So that's a very positive thing. But each chip has 12 2.2 gigahertz CPUs. It has 600 gigaflops of GPU power, which sounds great until you look at their training computer. It also has 2 NPUs that run at 37 TOPS, or tera operations per second per NPU. So this is pretty amazing. And all of this runs on only 36 watts per chip. I'm pretty sure the entire board runs on less than 100 watts, which is less than one traditional, old-fashioned tungsten light bulb. So this is all absolutely crazy nutty, right? My Intel MacBook has a 65-watt power supply. So you could almost run both of the full self-driving chips on that laptop power supply, which is just nutty.
The other thing I wanted to briefly talk about is I wanted to also mention briefly that this effort basically is incredibly vertically integrated in the AI team. So as I showed you, we own the vehicle and the sensing, and we source our own data, and we annotate our own data, and we train in our on-prem cluster, and then we deploy all of the neural networks that we train on our in-house developed chip. So we have the FSD computer here that has two SoCs, FSD chips here, and they have our own custom NPU, neural processing unit here, at roughly 36 TOPS each. And so these chips are specifically designed for the neural networks that we want to run for FSD applications. And so everything is very vertically integrated in the team. And I think that's pretty incredible because you get to really co-design and engineer at all the layers of that stack. And there's no third party that is holding you back. You're fully in charge of your own destiny, which I think is incredibly unique and very exciting. And then we have a deployment pipeline here where we take these neural networks and we do a lot of typical graph optimization, fusion, quantization, threshold calibration, and so on, and deploy it on our chip. And and this is in the customer's cars, and these neural networks run there.
And here we get some information about vertical integration. This is the secret sauce that literally nobody else has. Tesla has it and nobody else has it. Basically, it means that Tesla is fully in charge of their own destiny. We can start with the fleet. Tesla has its own fleet of cars. Tesla Artificial Intelligence Group helped to design the actual Hardware 3 boards in the cars right now, and it's specifically designed for what the AI team needs and nothing else. Also, Tesla has purpose-built this supercomputer to train the AI, and it's specifically to train the neural network models that the AI team needs and nothing else. And Tesla has internally designed the machine learning algorithms and the neural network models. Tesla has internally sourced, refined, and cleaned the data that they need, and nobody else can do this. I want to repeat this, no one else can do this. This level of vertical integration is the key to making full self-driving work. I want to take a moment to talk about leads. People think about leads in an analog fashion, right? Someone is 200 meters in front of me. That's something where I can imagine catching up a little bit at a time, right? What's going on here is totally different. This is more like a quantum lead. It's like an electron having to jump to the next shell in an atom. You've got an electron, right? It's here and it's got a certain amount of energy, and it doesn't just go like this to the next shell. It needs an input of a massive amount of energy from a photon before it can go whoop, and it just jumps there, right, instantaneously to the next shell. That is what's going on with Tesla and everybody else right now. Everybody else is in the low energy shell, the easy stuff, right? The low hanging fruit that they think is going to work well. But Tesla has boosted itself to the next energy level. You don't catch up to this a bit of a time. You have to put in a massive amount of energy. In other words, time, people, money, etc. to get there. Quite frankly, if I was on another AI full self-driving team right now, I would give up, or frankly, I'd go apply a Tesla, honestly. The years of foresight and the massive development costs that Tesla has put in are finally coming to roost here. No one without the same costs and time is going to catch up ever. It's that drastic. So if you take nothing else away from these two videos, it's that Tesla is so far ahead that nobody can catch up. It's not like they can incrementally catch up. They're going to have to go back to the drawing board and they're going to have to start over again to catch up. And meanwhile, Tesla is improving, right? So they're getting better and better. Frankly, it would blow my mind right now if anybody could catch up to this. But enough of that. Let's take a look at some examples that show how successful this new model is. And by the way, again, it sucks the video is so low resolution. I would love to be able to see all of these things better. There's a lot of information there that it's really difficult to see.
So the first example here, I have a video where this is on track testing. So this is an engineering car, and we asked it to slam on the brakes as hard as it possibly can. So this is a very harsh braking here in front of us. Even though it doesn't look like that in the video, this is very harsh braking. So what you can see on the right here is you can see the outputs from the legacy stack, which had radar vision fusion, and from the new stack, which is vision alone in blue. So in the orange legacy stack, you can actually see these track drops here when the car was braking really harshly. And basically the issue is that the braking was so harsh that the radar stack that we have actually ended up not associating the car and dropping the track and then reinitializing it all the time. And so it's as if the vehicle disappeared and reappeared like 6 times during the period of this braking. And so this created a bunch of artifacts here, but we see that the new stack in blue is actually not subject to this behavior at all. It just gives a clean signal. In fact, here, there's no smoothing, I believe, on the blue signal here. This is the raw depth and velocity that comes out from the neural net, the final neural net. that we released with about 3 weeks ago. And you can see that it's fairly smooth here. And of course, you could go into the radar stack and you could adjust the hyperparameters of the tracker, like why is it dropping tracks and so on. But then you are spending engineering efforts and focus on a stack that is like not really barking up the right tree. And so it's better to, again, just focus on the vision and make it work really well. And we see that it is much more robust when you train it at scale than something like this.
So this first example is one of extreme braking. You can see how the radar system, which is the orange track that kind of is jumping up and down, it loses the track. In other words, it keeps seeing a quote unquote new car over and over again that appears, disappears, appears, disappears. So it fails to brake hard enough early enough, which causes a huge problem at the end. On the other hand, the new vision system has smooth lines. That's the kind of purplish bluish line, meaning that it's tracking the car well the whole time and it's able to handle the situation very well. And guess what? This means that the vision system is better than radar. So think of that. This is not a poor substitute for radar that's just kind of good enough to work, right? And so we're being cheap and not including radar. This is way better than radar in this circumstance. And that is a powerful clue as to what's going on here. In other words, that's the power of Tesla vision.
Here's another example, fairly infamous example of slowdowns when there are cars going below a bridge. The issue here again is that the radar does not have too much vertical resolution. So radar reports a stationary object in front of you. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two. So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct. And then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then you brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case. Because we just get the correct depth and velocity, and vision obviously has the vertical resolution to differentiate a bridge from a car and whether or not the car is slowing or not.
And this example shows the classic phantom braking going on under a bridge. In other words, a large flat object. Note the spurious "oh crap" signal that the radar gives as it gets close to the bridge. Again, that's the orange one. And at the same time, the legacy vision system, which Karpathy says is not trained to a high enough standard in legacy as it depended on the radar, reports under velocity at the same time, and thus the car brakes hard for no reason whatsoever. And by the way, man, does my wife hate that. She will be happy to know that this will soon be a thing of the past. So what the new Tesla vision system can do is it can resolve altitude. In other words, it can know that the bridge is, quote, up there, so it doesn't have to worry about it, whereas the radar cannot do that. And thus, of course, we don't get any phantom braking going on under the bridge.
Here's another last example. We have a stationary approach. Again, this is in track testing environment. This is an example of a test that we would run. And we are just approaching this vehicle and hoping to stop. What you see in orange in the legacy stack is that it actually takes us quite a bit of time for us to start slowing. And basically what's happening here is that the radar is very trigger happy and it sees all these false stationary objects everywhere. Like everything that like sticks out is a stationary target. And radar by itself doesn't know what actually is a stationary car and what isn't. So it's waiting for vision to associate with it. And vision, if it's not held up to a high enough bar, is noisy and contributes sort of error. And the sensor fusion stack just kind of like picks it up too late. And so again, you could fix all that, even though it's a very gross system with a lot of if statements and so on, because the sensor fusion is complicated because the error modes for vision and radar are quite different. But here, when we just work with vision alone and we take out the radar, vision recognizes this object very early, gives the correct depth and velocity, and there's no issues. So we actually get an initial slowdown much earlier. And we've really like simplified the stack a lot and as well.
So this example shows another common thing, which is coming up on a stationary object in the road. Again, the radar is unable to determine if the object it, quote, sees is a threat or not, and the old vision system is not trained well enough to be a help. It was using radar as a crutch. So it only starts braking at 110 meters away from the truck, which leads to a very hard braking and a dangerous situation. Tesla Vision, on the other hand, sees the object at 180 meters away, and it slows consistently down from 145 meters away. That's a 60% increase in time and distance distance from the object, which creates a much safer deceleration profile. So these are all really, really cool examples. But then Karpathy goes on to talk about what Tesla does before passing this new system on to consumers, which, by the way, I assume means beta testers at this point, since we're not using it, right? Well, at least officially, it sounds like we're using it in shadow mode all the time, which is really cool. So we're actually driving the beta software, we just can't use it yet. So that's kind of a bummer. But anyway, it's cool to know that we're driving the beta software around in our cars right now.
We've extensively validated this before we, of course, ship this to customers. Just some example numbers for the validation itself. We've handpicked about 6,000 clips in about 70 categories of scenarios, like harsh braking, crossing vehicles, different vehicle types, environments, and so on. And we run these tests on all the commits of the build, and we run them also every day periodically as we were trying to drive up the performance on these clips. We also use simulation extensively for validation. We've also used simulation for training, although I haven't gone into that, but we've had some successes there. But we use it primarily for validation at this stage. And that's, again, like diversity of scenarios, trying to make sure that the stack is performing correctly. We've done a lot of track testing, and I've shown you some examples of that. We've driven this extensively in the QA fleet, and we've also deployed this in shadow modes and seen that this stack performs fairly well. So in particular, for example, for the automatic emergency braking, we actually see a higher precision and recall compared to the legacy stack that is a fusion stack.
Anyway, Tesla has come up with 6,000 unit test challenges. So you can think of it like Survivor or something, right? It's got 70 categories of scenarios, and they run this every day to make sure that full self-driving is consistently getting better and not getting worse in any category. So basically, you can think of this as a full self-driving test that they can challenge the full self-driving software with each version and each day to sort of baseline how well it's doing in each circumstance. And essentially what you want is for it to improve in each circumstance and never get worse in any of them. They also, interestingly enough, have simulation testing, which I find interesting. He doesn't talk about that much, but that's just an interesting little side fact. They've also got actual track testing with real vehicles, putting it through very specific scenarios to cover different situations, etc. So basically, it sounds like that's a quality assurance thing that's being done by engineers. And then, like I said in episode 1, they put it in shadow mode and let it drive around with drivers. And in the last 4 months, it sounds like they've done 7 times around this wheel, again, that I covered in episode 1. And that's about 1,000 years worth of driving. And there's one little detail here that's really cool. The AEB, or automatic emergency braking, shows that it's higher precision and recall than the old system. What that is, for people who don't know, is those are statistical metrics that quantitatively measure how well something is working. So what that gives you is fewer false positives, like phantom braking, and fewer false negatives, like not braking soon enough when it should. Anyway, all of that is a super good sign that they have quantitative measures that show that it's improving. And guess what? In the end, they have actually released this to drivers.
And so having seen all this, we've actually released this. We've accumulated about 15 million miles so far. And 1.7 million of those have been on autopilot. And so far, there have been no crashes. Now, of course, we're running at massive scale here. And so we do expect some crashes at some point. The legacy stack has a crash roughly every 5 million miles or so, I believe. And so we do expect some incidents at some point. But the improvements for the vision stack are not sort of stopping. So I think we're very confident that we're barking up the right tree here, and that we can actually get this to work really incredibly well.
So as the slide shows, there's been 15 million miles driven with this software on the cars. 1.7 million of that is on autopilot. They've had 0 crashes. Again, 0 crashes. Boom. Or wait, not boom. 0 crashes is not boom. Anyway, as an interesting aside, the legacy stack, which is the old system, has a crash every approximately 5 million miles of driving, or again, about 10x safer than human beings already, and that's the legacy stack. And this one so far is showing that it's even better. And very importantly here, Andrej says that the improvements are continuing. In other words, the error rate is continuing to drop, which means the model is continuing to improve in training and testing. And this, by the way, is absolutely huge. If the validation tests ever flatline or even start back up again, what that means is your system is finished. It's basically as good as it's ever going to get with this model and this data. So the fact that it's continuing to improve is huge. That means that this system is going to get better and better. It's not as good as it will ever be. It's actually continuing to get better and better. So that's just massively important information. It's a little thing that anybody outside of AI work is not going to realize, but I recognized it as soon as he said that. I was like, oh crap, that is a massively important statement. And finally, Karpathy talks a little bit more about data. Interestingly enough, the auto labeling is being done at scale and very successfully for non-vehicles, like pedestrians, as Karpathy shows. This is offline, remember, so that means it's just for labeling. It's not being done in real time. Accuracy in this case is much, much more important important than speed here. And also this system gives the ability to recreate, quote, LiDAR scenes using only vision. In other words, like pseudo LiDAR. Again, remember this is not being done in real time. It takes a lot of processing and time to do this, but it's creating this. But the important part of this is that they can utilize this information to determine the most important tasks the car itself needs to do in a time-critical fashion, and then they can focus on the important tasks that the FSD computer has to manage. And this gets to one of my favorite acronyms, KISS. Keep it simple, stupid. In other words, do the complicated stuff offline and at the beginning, and do the simple stuff at the end. So identify actionable elements and reduce the model to acting on those things, which is a huge benefit to offline training. One viewer at the end asked an interesting question. He asked if vision was enough for every circumstance, or specifically, would thermal cameras be useful for Tesla?
Like clearly people use vision and the visual spectrum, and they make it work. And so there's an infinity sensors of varying economic costs. Actually, vision and in the visible light spectrum is incredibly cheap sensor, right? So the economics of this are very appealing, and you can actually manufacture and include this at scale. So it's a very cheap and nice sensor. And I would say that basically we have proof from humans that it is sufficient. And I would say also that vision has all of the information for driving. So I would say that basically vision is necessary and sufficient in my mind. And so we're primarily focusing on that. And you could go crazy with a lot of sensors, but I think we're definitely currently just like doubling down on that alone.
And as Karpathy said here, while other sensors and things could be very useful, visual cameras are very cheap, they're easy to deploy at scale, they have a ton of information, and so while it might be cool or warm for a thermal camera to be there, it's not necessary. Vision, as he says, is necessary and sufficient. It's necessary to do the job, and you don't need anything else to do the job.
So in summary, what I try to argue and give you a sense of is vision alone is actually, is our finding that is perfectly capable of depth sensing. It is an incredibly rich sensor in terms of bandwidth of information. And doing this and matching radar performance and depth and velocity is incredibly hard. I believe it requires the fleet because the data set that we were able to achieve was critical in all these performance improvements. And if you do not have the fleet, I'm not 100% sure how you can source all the difficult and diverse scenarios that we did source, because I believe that was critical to getting this to work. So it's hard, it requires massive networks, a supercomputer, and a data engine, and the fleet. But all of these components are coming together in a vertically integrated fashion at Tesla AI. And I believe that this makes us sort of uniquely positioned in the industry where we are barking up the right tree, and we have all the puzzle pieces to make this work.
So what are Karpathy's overall conclusions? First, Tesla Vision is capable of replacing radar and doing a better job of it. In order to make this work, it takes massive data, and it's hard to do, but it's the right way to go. And Tesla uniquely has all of the puzzle pieces to make this happen. And a shout out to everybody else out there. I don't know how you're going to be able to do it without the fleet that Tesla has. So in short, vertical integration and years of foresight and planning and money and investment have led to this moment. And yes, boy, is this a big moment. It's not out for all of us yet, but it sounds like full self-driving is solved at this point, and it's just a question of getting it a little bit better and making sure it's tested and making sure there's no weird glitches before it rolls out to the fleet. This is huge news. Again, not a financial investor, not a financial advice, do your own research, but as soon as we get our house sold and everything, I'm spending every penny that we have to buy Tesla stock because people don't realize this yet, and they have no idea how important this is going to be, and they have no idea how nobody else is going to catch up to Tesla at this point. All right, I hope you enjoyed this episode and found it fun and informative. I know I kind of ended up sounding like a Tesla fanboy at this point, but I want you to understand this is something that I work in. This is something I understand, like, you know, from the inside out. I've done a lot of research in AI, and what I'm hearing from Dr. Karpathy in this case is so mind-blowing that it's telling me that Tesla basically has solved this problem. And if you don't yet realize how huge that is, you will within the next couple of years. I guarantee it. It's going to be world-changing. So anyway, I'm not being a fanboy here. I'm just super excited about something I understand and a lot of people don't understand. But anyway, if you did enjoy this video, even if it was a little over your head at points, definitely like it so other people can find it, and certainly consider subscribing for more of this. As always, of course, a huge shout out to my patrons on Patreon. You all are wonderful. You really make this possible. You make it possible for me to spend time. You know, these episodes episodes take a huge amount of time on research and filming and editing, etc. So you all really help to make this a possibility, and I thank you from the bottom of my heart. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And don't forget about our merch store, which now has "Physics is the Law, Everything Else is a Recommendation," which is a quote by Elon Musk, as well as other t-shirts, mugs, tumblers, etc., etc. Check it out in the description. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how clicking on a link and going shopping for a car, a solar roof, a battery wall, or anything on Amazon helps out the channel. I really appreciate it. And as always, feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.